Hello, everyone. We're excited to welcome Ariane Sullivan, who will be the speaker for today's webinar, A Practical Guide to Maximizing the Reversed Phase LC Separations Peak Capacity. My name is Alex Nase, and I'll be moderating today. If you have any questions during the presentation, please type them in the chat window and include your name and company, and we'll do our best to answer as many questions in the allotted time slot as possible. If you miss anything or would like to review content, you'll be able to watch a recording of the webinar and view the slides on our website. I will also send out a follow-up email that will have the links to those. Before Ariane begins, just wanted to give a little background on MacMod. We're a chromatography company that offers scientists innovative solutions for their complex separation needs. We recommend and supply the best columns and accessories to our customers. We also provide application notes, technical reports, white papers, and other up-to-date resources from industry-leading scientists to keep you informed. Today's speaker is Ariane Sullivan, and she's a product specialist at Avantor Sciences. Her high-profile academic appointments with the eminent professors George Guillochon, Peter Carr, and Andrew Schalaker have amounted to over 15 years of global collaborations with fundamental and applied laboratories, companies, and over 50 peer-reviewed publications. She's passionate about continuous learning and sharing of knowledge, diversity in STEM, and sustainability. Thank you for joining us today, Ariane.
Thank you. Thank you for the lovely introduction, and thank you for the opportunity to speak with everyone today. And I do want to share that it's a topic close to my heart because I had the pleasure of working with some scientists at Avantor, and at the same time, it really focuses on a lot of the work that was completed when I was a postdoctoral associate in Professor Peter Carr's group in Minnesota. And with that, I'd like to begin the presentation. I'll pop the camera back on during the Q&A. So the outline of today's presentation, there's 3 different sections. Firstly, I'd like to go through the background. And once I set the scene, I'd like to jump into a lot of the different trends between peak capacity and all of the different operational and practical parameters that we all have control over when we're developing a method. And then finally, I'd like to share with you 2 very practical and general approaches that have been published from the group of Professor Peter Carr, one being on the relatively larger peptide complex samples, and then a focus on the small molecules, so a complex small molecule general approach. The key takeaway message for today is really to arm you and give you the insight on how you can take all this information and use that to your advantage whenever you have a new sample come across your laboratory desk, and for you to be able to maximize the separations peak capacity in a very rapid fashion. So with that, let's jump into the background. I'm sure for all of the separation scientists and the chromatographers on the call today, you would have experienced in one form or another that this exercise method development is very, very, very expensive. It exhausts a lot of our time, a lot of our consumables, and also it demands a lot of our expertise, especially when the samples become more complex. And we have to, as separation scientists, we have to appreciate that there is a multivariate relationship between all of the practical parameters that we have control over in the laboratory when we develop a method. That is gradient time, Tg, temperature, T, flow rate or velocity, which I'll symbolize as F, and also the final mobile phase composition, which I'll represent as V final. So once we begin and appreciate the trends between all of these practical parameters, then we can start understanding and appreciating how to develop methods in a very fast and rapid way. And the best approach and the approach that we're going to look at today is to maximize the peak capacity for our sample separations. In this example, in this slide, I'd like to showcase a really excellent chromatogram and illustration of how we as separation scientists can exploit not only the peak capacity of our liquid chromatography separation technique, but also hyphenating that with a high resolution technique, such as mass spec. And when we really do exploit all of the technologies that are accessible to us as scientists, as well as using our knowledge on how to develop a method, not only for the LC, but also the MS, then we can exploit these techniques and obtain these sorts of separations. For example, here we showcase an analysis of 300 pesticides. And hopefully today you can have some insight on how to maximize the sample peak capacity in a rapid fashion. So I've said sample peak capacity a few times now, and here I'd like to show you just a very simplistic way of describing sample peak capacity, where I'll symbolize it as N subscript C, and that's equal to the separation window. So that's going to be defined by the solutes in your sample and dividing that by your average peak width in your chromatogram. And here I'd like to show the equation in a bit more detail with the maths and the chromatogram that we see. This was taken from a paper by Snyder Dolan, very famous names and highly respected scientists in our community. And also I do want to point out that also a scientist from MacMod was also included in this publication. So let's go back to the equation. So we can use our chromatogram and we simply take the retention time of our last solute of our sample, subtract that with the first retention time of our solute in our sample, and divide that by the average peak width. Here I've taken 4 sigma. There are some cases where other people and other scientists might take 1 standard deviation or 2 standard deviations. That's all well and good, but please take into account that when you do take the peak width at half height or less than 4 sigma, you may miss the comprehensive peak shape attributes that are close to the baseline, where 4 sigma really takes into account those sensitive baseline effects with your peak shape, for example, peak fronting and peak tailing close to the baseline. So please, I recommend you to take that 4 sigma approach because that will give a really comprehensive metric for your average peak width. So let's jump into a chromatogram. So let's take that first chromatogram with the 300 pesticides and let's calculate the sample peak capacity. So here we take the last retained solute, the retention time, and the first retained solute. So we subtract that and we get 20.8 and we divide that by the average peak width. You don't need to measure every single peak width of this chromatogram. You can use the software output and that result report out. You do have control if you want to go deeper into that software and see how it calculates the average peak width. You can tell your software to either take a 4 sigma approach instead of your peak at half height. So take that average peak width, divide that number or that separation space that your solutes of interest occupy. And for this chromatogram, you can see we get a value of 83. And what that represents is we can separate with a liquid chromatography separation technique. We can resolve 83 peaks side by side with this method, with this column, and with this detection technique. So in this slide here, I do want to illustrate and give you an overview of the roadmap for all of those equations that really govern gradient elution theory for reverse phase liquid chromatography separations for specifically low molecular weight or small molecule samples. So while it might seem very intimidating, just know that as you gain more experience in the lab, in the practical sense. And when you read more about gradient evolution theory, I do want to tell you that you will start grasping and understanding these equations in one form or another. But very quickly, just to understand that multivariate relationship between all of these practical parameters that we have control over when we develop a method, you can see when we toggle with these practical parameters, it really influences a lot of the different equations that govern reverse phase gradient evolution theory. In one way or another, it's going to affect the peak shape. Here we've got sigma, so a metric that describes the peak width. And also when we change any of these practical parameters, we also change the retention times of our solutes. And this is why we feel quite frustrated when we develop a method. There's a multivariate relationship. It's really complex. And it's just a real quick insight into the maths behind method development, particularly gradient evolution theory. And if we see we affect the peak width and we affect the gradient time, hence we do affect the sample peak capacity, because that is effectively the retention time of the last and first peaks of our solutes in our sample divided by that average peak width. I do highlight these two papers on the bottom. Please, I recommend you read this in your own time to improve your understanding for gradient evolution theory. So before I move on, I do want to share with you, as much as I did a lot of experimental and empirical experiments in the laboratory during my postdoc in Professor Peter Carr's group, I also did a lot of experiments to develop a really good computational approach, because we needed to model the retention times and the peak widths in a very good fashion to mimic what we were seeing in the laboratory, because we also didn't want to exhaust too much consumables and time spent with experiments, empirical experiments. We wanted to drive forward this project with a good computational approach. So there were three aspects that were really important to integrate. The first one being we needed to definitely capture the retention times as we change the temperature environments for our separations. And the linear solvent strength model really served us well, and we had to integrate dependence for the different temperatures. Also, because we're looking at small molecule separations, we also wanted to integrate a factor or a part of the computational strategy that also took into account whenever we change the column length and the velocity of our separation or the flow rate. So the Van Diemter equation was really good into integrating this into our computational strategy. And finally, because we were toggling and changing that temperature environment, we had to also integrate an aspect that took into account the viscosity changes, because of course, when you increase the temperature, you decrease that viscosity effect. And the Chen and Horvath approximation really served us well. And again, also another aspect, because we're changing that temperature environment, we also wanted to integrate the diffusion coefficients, which has a dependency on temperature. And we wanted to capture that those mass transfer kinetics between the solutes, the stationary phase, and the mobile phase. So the Wilkie-Chang approximation was really good. And again, I just highlight a paper for further reading. So we did do a lot of experiments, I would say hundreds of experiments in the laboratory. And we used that to build and to confirm that we had a correct computational approach. And here I only include a very limited and snapshot of those few experiments that we performed. And I do stress we did hundreds of experiments. So here we've got different temperatures, different gradient times, and here you can see the experimental times and the predicted times with the computational approach. And you can see they're in very close agreement. So with that, we were happy with the computational approach, and we used that, we exploited that to do many more calculations and experiments to help us understand the trends between peak capacity and the practical parameters that we have control over during method development. So now I jump into the second section of the talk, where we look at the trends versus peak capacity and those practical parameters, gradient time, temperature, flow rate, and the final mobile phase composition. So the first slide I'd like to highlight, I'm looking and showing results for complex, relatively larger molecules. And I do want to touch on, while I'm highlighting here fixed column length, if you know a bit more about the linear solvent strength theory, you will know that for the relatively larger molecules, they do have larger S coefficients. So that allowed us to fix the column lengths. So for these infographic and the results shown here, we fixed the column length and we wanted to look at the effect of gradient time. On the y-axis, we've got peak capacity increasing as we go higher. And on the x-axis, we've got gradient time increasing as we move to the right of this axis. And very intuitively, with these data points and results, you can see as we increase the gradient time, we do obtain an increase in peak capacity. I also want to highlight this was represented not only with a computational results from the study from Zhao Li and Professor Peter Kai in 2006, but also with some experiments that Matt James did with a BSA tryptic digest in the lab. Also here, I just flashed onto the screen the peak capacity. There are other equations to calculate this. And here we denote this equation with P subscript C. And this is when we take the gradient time and divide it by the average peak width +1. And you'll see in the next slide with the chromatograms of peptide separations. They're very complex and they occupy a lot of the separation space of the gradient time. So when you do occupy most of the gradient time, this is a good equation to take. But if you don't occupy all of the gradient time, I do highly recommend you use that N subscript C equation. So in this slide here, still focusing on those complex, relatively larger molecules, here looking at the BSA tryptic digest. Again, we fix the column length and we want to look at the effect of the velocity flow rate in these chromatograms here. On the top chromatogram, we have the slowest velocity that we had confidence with. Definitely, whenever you're doing your experiments, make sure you understand the lowest velocity of your instrumentation. So here we chose 0.21 mils per minute, and you can see a peak capacity for this separation of 283. On the bottom, we have the highest velocity that we were willing to go up to, which was 0.5 mil per minute, and we obtained a peak capacity of 300. Then we did some other data points in between the slowest and the fastest velocity that we defined. And here we just showcase one of those medium data points of 0.35 mils per minute. And you can see that there is a maximum of peak capacity obtained for this medium flow rate. And what this means is for complex, relatively larger molecules, we can't simply increase our peak capacity by increasing our flow rate. We do need to do some systematic experiments and understand where that medium velocity is, because that's going to define the highest peak capacity achievable and obtainable for our method. And we definitely want to make that flow rate decision near that peak maxima or that peak capacity maxima. So now I'm going to shift focus. We're going to look at complex small molecule separations. So here we do fix the column length, and we're looking now at the effect of both the flow rate, the velocity, and the gradient time. So the same axis for peak capacity on the y-axis, and here we've got the velocity on the x-axis. In the different trend lines here, I do represent the different gradient times. So in red, we have the shortest gradient time of 15 minutes, in black 30 minutes, blue 60 minutes, and the highest in green for 2 hours. And I'm just going to take our focus to these gradient time trends. And you can see there's no intersections for any of these trend lines or these gradient times. And what that means is we can simply make that decision make the longest tolerable gradient time decision, because you won't sacrifice any peak capacity. In fact, as you increase that gradient time, you're going to obtain a higher peak capacity. So looking at the velocity, you can see with all of these trends, you do not sacrifice any peak capacity as you push that velocity as fast as possible. There may be a slight maxima in peak capacity for the 2-hour separation. However, as you push that velocity faster and faster, you don't have a significant loss of peak capacity. So for the small molecules, it's easier for that velocity decision. You simply have to push it as fast as possible, compatible with your column and compatible with the back pressure limits of your system, because you will achieve the highest peak capacity. Because of the trend differences between the small molecules and the relatively larger peptides, we had to do a root cause analysis to understand what was behind these different trends of peak capacity versus flow rate. We did a lot of experiments and calculations, and I just want to show you the results and why there was a change in trends. So we eventually found that by repeating all of these calculations for the small molecules, but simply changing the diffusion coefficients of the small molecules with the peptides, we then repeated those calculations, and you can see again, there is a distinct maxima in peak capacity versus flow rate by simply replacing those small molecule diffusion coefficients with those peptides. So what this means is when you're developing a method for peptides, you do need to do experiments, some systematic experiments, a slow velocity, a fast velocity, bracket that with some different systematic data points in between. You need to know where that maxima in peak capacity is, because you need to choose a flow rate around this region. For small molecules, you're okay because that velocity decision is easy. Just simply push that as fast as possible. I'm just going to take a sip of water. And now I'm going to jump into the different optimization strategies. And I'm going to emphasize this is for small molecules. So we use that computational approach for 3 different case scenarios, in green, in blue, and in black here. And in those different case scenarios, we use that computational approach, and we told the strategy, maximize these variables, these practical variables, optimize these variables while searching for the highest peak capacity possible. So you can see with the different case scenarios, in green, we have the largest number of variables to optimize. In blue, we only have 2 variables, and in black, we've only got 1 variable. And also, what we also want to represent here is the peak capacity versus different temperature environments. So you can see the best possible case scenario is when we develop and optimize a method for the largest number of variables, and also when we increase the temperature. So here we have that case scenario in green where we optimize the largest number of variables, the final mobile phase composition, the velocity, and the column length. Yes, we need to optimize the column length for small molecule separations, because you can see it clearly obtains a higher peak capacity than the other 2 case scenarios, where in blue we only optimize the final mobile phase composition and velocity, and in black only the final mobile phase composition. So you can see for these 2 other case scenarios, we also do have an increase in peak capacity as we increase the temperature. We do have a slight plateau after we push the limits and the temperature above 80 degrees Celsius. But I would emphasize that there's not many chromatography groups out there around the globe that pushes beyond 80 degrees Celsius. So from here, what we can take away is, in order to optimize and increase your peak capacity, we do need to increase that temperature. And I do want to emphasize, please move out of your comfort zone, because when you increase that temperature, you can clearly see for all these 3 case scenarios, you're going to increase that peak capacity. Also, again, I mentioned it previously, when you increase that temperature, you are going to decrease the viscosity effects with your liquid chromatography separation. You're going to decrease those back pressure that's observed on your system. And also you're going to have better mass transfer kinetics. So please move out of your comfort zone, increase that temperature to as high as possible. Obviously, you want to make sure that it's compatible with your column, your stationary phase, your system, and also all of the accessories and connections that are exposed to this temperature environment. So with that, I'd like to jump into the last section of the talk where I'll share two really good practical protocols or general approaches for optimizing the peak capacity, maximizing the peak capacity for complex samples. So this first protocol, this was published back in 2006, and this comes out of the work from Xiaoli Wang and Professor Peter Carr. It was published in 2006, and I do emphasize it still is fundamental, and it drives and it gives you a lot of comprehensive understanding with optimizing the peak capacity for gradient elution theory and practice for reverse phase separation. So please take a look at this paper. And I do want to share with you, while it looks really simplistic and elegant, it's only 4 steps on the screen at the moment. I do want to walk you through this this elegant and 4-step protocol, because there is a lot behind this. Of course, they did a comprehensive study. They looked at the multivariate relationships. They looked at experiments in the lab. And I do want to state, before we even go into that first green sentence, you do need to complete a column selectivity study. So please, before you take a look at this protocol, this very easy 4-step protocol, please make sure you go through a column selectivity screening, which is really important for any approach to reverse phase separation. So we will know as separation scientists, as chromatographers, that selectivity is key for optimizing your resolution. So please tune and optimize that column selectivity in your column selection decision. So you've really made that empirical and best decision for which column you're going to enter and start this protocol for maximizing your peak capacity. So grab that column, and it marries very nicely with this first decision, fix that column length. So do that column screening study and simply take that column and fix that column for this 4-step protocol. So the first decision you want to make, this is selecting the maximum allowable gradient time. And while it seems very trivial on the screen right now, I do want you to take a bit more responsibility with this decision. Please take a discussion with your laboratory manager, with the other members that use that system that you want to use for your sequence and your project. So understand how much time do you have on this system to dedicate to your project, to your sequences, to every single injection, because that will now give you a more objective and scientific decision and arrive at this first decision that you need to make with more responsibility. So please select the maximum allowable gradient time for each injection that you can dedicate to every injection in your sequence. After that, you need to select the highest tolerable temperature, as you saw with those trends. And as now you know, because I keep reiterating this message, select the highest tolerable temperature. You're going to decrease the viscosity, you're going to decrease the back pressure, and you're going to give and benefit from the mass transfer kinetics with the highest tolerable temperature. Please make sure it's compatible with your column, your stationary phase, with your system, and the accessories and connections that are exposed to this temperature environment. The third decision, as you saw with those trends in the second part of the talk, for peptides, you do need to optimize this flow rate. So please do some systematic experiments, understand the slowest velocity that your instrument can deliver with accuracy and precision. Use that as your lower bracket. Use the highest velocity that you're comfortable with, compatible with the back pressure limits of your column and your system, and then take some data points in between. Understand where that peak capacity maxima is and make sure you decide that flow rate decision based on that maxima that you see in peak capacity. And then finally, the final choice that you need to do, and while you saw that the peptides are complex and they occupy much of that gradient time, you do want to exploit all of that gradient time. You don't want any dead time after your last eluting species and the end of your gradient. You want to exploit all of that separation time because time is precious for your lab. So please adjust that final mobile phase composition so your last eluting species of your sample elutes at the end of your gradient. And that is the practical approach for maximizing the peak capacity for complex peptide type separations. So with the small molecules, I do want to highlight that we do have a bit more decisions to make because we need to guide the decision of yes or no, do we have the correct column length for our sample separation? And before we even move into that, I do want to share with you a really classical test that we should always be doing. And I think we all would intuitively be doing this test. So basically, I want to share with you the Snyder-Dolan test. It's a classical test. And basically, it's a screening gradient from 5% organic modifier to 100% organic modifier, or in other words, 5 to 100% mobile phase B. So this is a screening gradient. Snyder-Dolan, they developed this because this was for us to exploit, because this test is going to guide us whether or not do we do gradient or isocratic elution conditions for our separation. This will come in handy. So yes, we use it to understand whether or not our sample is complex or not, complex enough. Do we do gradient or isocratic? But also it's very important in our protocol for small molecule peak capacity optimizations because it will guide our column length decision. But let's go back to this protocol. You need to run the Snyder-Dolan test and you need to run the sample of interest. Please do not use a standardized test mixture. Use your complex sample. You run that screening gradient, and then we need to use the Snyder-Dolan test criteria to determine if we move forward with a gradient elution separation or do we use an isocratic separation. So to pass the SD test, we have this criteria, and I'll show you an example of when we fail and when we pass in the next 2 slides. So if we do pass, yes, gradient elution theory is appropriate. So we need to go forward with that decision tree, which I'll share with you in a few slides. And if we fail this criteria, we can't maximize the peak capacity with that decision tree. Instead, you need to simply optimize the isocratic mobile phase conditions. So here, let me walk through you and show you a chromatogram which exemplifies when we fail the Snyder-Dolan test with our sample. So here we do a gradient separation screening, 5 to 100% B, the Snyder-Dolan test, and let's look at that last eluting species, our first eluting species, and divide that by the gradient time. So we do that maths and we get a value of 0.18. And taking that criteria of the Snyder-Dolan test, you can see that it fails this criteria. So what this means is our solutes occupy 18% of that gradient window of 5 minutes. We do not follow that protocol to maximize peak capacity, and we need an isocratic mobile phase separation technique, which isn't too bad. Actually, good news for you, that's great, because then you don't have to waste time on re-equilibration. You can simply stack your injections one after the other. So let's look at an example where our sample does pass the Snyder-Dolan test criteria. So we have our last eluting species, our first eluting species, and we divide that by the gradient time. And you can see there is a bit of a delay because I've taken into account the system delay of the gradient as well as the T0. So looking at the maths, subtracting the last and first eluting species and dividing that by the gradient time, we have a value of 0.43, and that does pass the Snyder-Dolan test. So our solutes occupy 43% of that gradient window. So we proceed with the decision tree to maximize peak capacity, because this sample does in fact require gradient elution separation conditions. So here we have the decision tree, and this does represent what was studied comprehensively and outlined in that publication from the postdoctoral work from Professor Peter Carr's lab. However, I really do appreciate this chance to talk in a virtual fashion, because while reading a paper is nice, it can be distracting, and by showing and sharing this decision tree of separation decisions, I can tell you a bit more about the story behind each of the steps. So again, very similar to that peptide protocol, please conduct a column selectivity study and column selection decision, column selection decision study before you enter this protocol. So please, separation selectivity is key to maximizing resolution. So please exploit that selectivity or chemistry of your column. Once you know which selectivity you want to use, now you can enter this peak capacity protocol. So again, similar to that gradient time decision, please have a decision, take more responsibility in this gradient time decision. Talk to your lab members who are sharing that instrument that you use. Understand how much time you can dedicate to every injection for your sequence, and that will give you a very good number or gradient time to choose for this first decision. And of course, choose a column length. I'm not going to tell you which column length you need to choose, but I will tell you the easiest column length decision is basically take that column that you used with your column selection study that you did before. So choose your gradient time, choose that column length. And then, of course, I'm reiterating it again. It's very similar to that peptide study. Increase that temperature, move out of your comfort zone. Your separation is going to thank you. You're going to decrease the viscosity, decrease the back pressure. You're going to benefit from the better mass transfer kinetics. So increase that temperature to the highest tolerable between your column, your stationary phase, your system, and the connections and accessories that are exposed to this temperature environment. Then here, while if you were keyed on and you remember, push that velocity as fast as possible, please be reserved. Don't do that yet. We need to choose a reasonably sensible flow rate now, because the first decision, understanding that multivariate relationship, the first decision we need to make is, do we have the correct column length, yes or no? So choose a flow rate that's sensible, and I would recommend choose the flow rate that's on the certificate of analysis with your column. If you don't know what that is, if you've lost that certificate of analysis, you've got a serial number on that column. Call your column manufacturer and understand what that certificate of analysis flow rate is, and choose that velocity, because we do need to address this question with a Snyder-Dolan test. So is the column length sufficient? We do the Snyder-Dolan test again, 5 to 100% B with our sample. However, we do put a stricter criteria. We need to put this 0.4 or 40% criteria, because this will give you a very clear-cut yes or no, do we have the correct column length? If we fail this criteria, then we need to increase that column length. So how do we increase that column length? We can't do any magic. We have to take a practical approach to this. So take a look at your column storage or your column shelf and look, do you have a column of the same selectivity with a longer column length? If not, maybe you have a column coupler and you can couple two columns of the same selectivity and increase that column length in that fashion. And if not in that way, which are two very accessible ways in your laboratory, if you can't do that, give a call to your column manufacturer, let them know, I want this column selectivity, but I want a longer column length. What can you provide me with? So increase that column length and repeat this side of the decision tree again until you pass that Snyder-Dolan strict criteria of occupying 40% of that gradient window, of that gradient time. So when you do pass, yes, you have optimized the column length, and this is the biggest part of the decision tree, because then, yes, you can go back to what we've learned in those trends between velocity, push that velocity as high as possible. Of course, please be sensible. You need to take into account the back pressure limits of your column, your system, and those accessories that you're using. I would definitely, if you can, use better accessories, use a better system, and use a higher back pressure limit column, because you're going to achieve higher peak capacity. And then the final decision, very similar to the peptides, you want to exploit all of that separation space in your gradient time. Don't leave any dead space between your last eluting species and the end of your gradient. Please exploit all of your gradient time. Adjust that mobile phase final composition so that last eluting species is right at the end of your gradient time. And so that is I don't think you're going to get all of that story in the paper, but please use this webinar. It's going to be available on demand through the MacMod website. So looking at the robustness of the protocol, so we did 20 different combinations with a very complex sample of small molecules with different gradient time and column length decisions at the very beginning of the decision tree. So we used the decision tree, that protocol optimization, went through it, and we compared it with that computational one-step solver optimization. So looking at the computational approach, one step told it to optimize all of those practical parameters while maximizing that peak capacity value. And you can see with 20 different tests and combinations of gradient time and length, it's very trivial, the differences between the decision tree and the computational approach of a peak capacity of 3%. So we were very happy. The maximum differences in velocity and phi final is very small, and the peak capacity very small. So we were very confident that the robustness of the protocol will serve you well whenever you have a new small molecule sample of interest. When that changes, just follow that decision tree again. So the last slide, of course, we wanted to apply it. We wanted to apply it not only computationally, but go back into the lab. We did exhaust a lot of consumables before we had the computational approach, but let's go back in the lab and let's see what it looks like for a very, very complex sample. And I'm just going to highlight from Professor Peter Carr's group. I think many chromatographers know Dwight Stoll is really flagshipping and championing 2DLC separations. So I had readily accessible to me very complex samples that I used for 2DLC separations. So I use that for this decision tree of separations for a 1DLC approach. So I took that sample, very complex, used that decision tree, and arrived very quickly at this gradient time, column length, temperature, flow rate, and final mobile phase composition. I did delay the injection of the sample because I wanted to make sure my first eluting species was coming out after the delay time and the T0. So you can see that with the front of the chromatogram. And also you can see I've exploited all of that gradient time space, where at the end I have my last eluting species at the end of the gradient. So to compare the peak capacity, I took that really complex, messy sample sample of interest for 2DLC separations, the maize seed extract, and we looked at the median peak width. So here we have the median peak width of the maize seed extract, and we compare it to a very, very clean standard set of compounds of indoles. And you can see the median peak width was very similar. And if you can remember the peak capacity equations, it has the gradient time or the separation time of the last and first eluting species on the numerator, and in the denominator we have the peak width. So having very good peak widths and in agreement, we were really happy, and we were sure that the application of the protocol did apply and was successful in the laboratory. So we achieved a peak capacity of 170 for this 15-minute separation. And if you compare it to the first separation for those 300 pesticides, that achieved a peak capacity of 83. So here we're really happy with this peak capacity value. And with that, I wish you all the best of luck. Now you have a lot more insight into gradient elution theory for reverse phase conditions, and the stories behind those papers that really comprehensively and elegantly have a really boiled down protocol to maximizing the peak capacity for peptide and small molecules. So I wish you all the best of luck. When you come across a new sample, a complex sample, please use this information and use those practical guides to maximize the peak capacity in a rapid fashion. And I'd like to thank a big thank you to MacMod for calling out to me and letting me share this really good and still very relevant study with peak capacity optimization. And definitely a big thank you to everyone who contributed to this talk today. And of course, a big thank you to all of our listeners and attendees. Thank you for your attention.
Thank you, Ariane, for that wonderful presentation. We do have a few minutes to answer questions from the listeners. We would like it to be interactive, so if you do have a question, please type it into the question area and we will make sure to get as many questions in as we can. Please try to include your name and company. That way, if we don't get to every question, we can follow up with you. So let's move into the Q&A. Okay, first question. Are you suggesting the protocols in your talk to be used instead of QBD, QSSR, or QSRR, or other computational approaches?
Thank you for that question, and thank you for the listener who's breaking the ice and bringing that question in. Those are very good question, thank you. And I think quality by design, quantitative structure, and any resolution mapping and computational strategies that you have if you have access to that, I would recommend please use that. We are at the day of an age that time is precious, so use as much information and strategies that can help you develop. And the more you use, the better and more robust you can have confidence when you develop a method. However, as you can see with these separations, a lot of this will guide you with your first insights with complex samples where you don't necessarily know all of your target peaks. Perhaps they may be unknowns. For example, they may be included in your sample matrix, but you have no idea about them, but you still need to separate them and resolve them for better chromatography, better ionization. So please use this to maximize your peak capacity for your LC strategy. And for sure, use other computational strategies at your at your will, because it's going to definitely improve and create a more confident and robust method, which you definitely want when you finalize your method development stage and enter into a validation stage. Thank you.
Okay, I think this question may be for a specific example you went over, but it says for the SD test, where is the 25 to 40% from?
The 25 to 40%. So maybe, am I still sharing my slides? Can I go back?
Yes. Yep.
Excellent. So that's a good question. 25 to 40%. And you need to take this mathematical equation. So this is going to be where your solutes occupy your gradient time. So for this sample here, we define that by the last retained species at 3.2 minutes, subtract the first eluting species at 1.05 minutes, then take that value and divide it by the gradient time. So if I rewind it a little bit, we've taken our sample, we've done a Snyder-Dolan test of 5 to 100% B, we've defined the gradient time of 5 minutes. So now we need to look at our chromatogram, look at the solutes, the last and first, take that, subtract that, divide it by the gradient time that we chose. And then now we have to look at that 25% to 40%, or 0.25 to 0.4 minutes. So this was studied and this was recommended by Snyder-Dolan. So definitely take a look at this reference. It will go into depth why they've taken this, and definitely there are gray areas, but definitely this is where I've taken that 25% to 40% or 0.25 to 0.4 minute window from.
Okay. Next question. The optimal velocity you suggest in the protocol differs from the Van Deemter optimum. Can you go deeper into this?
Yes, it does. And I can go deeper, but let's jump back and let's talk about Van Deemter optima. So Van Deemter optima, it's looking at H versus flow rate under isocratic conditions. So that's the key there. They are just looking at a set of closed experiments for fixed isocratic conditions, while here we're looking at gradient elution theory, where you can see maybe here we have the Van Deemter optima, but we have many other equations that are going to pull the peak capacity in different directions. We have things that you jump into here and you might catch if you're more expert, you have more expertise in gradient elution theory. We've got definitely the peak compression factor when we have the gradient peak compression effects. So that is going to change the peak width respect to the gradient elution theory, which may not lie and be in agreement with the velocity and the peak width of the Van Deemter equation and curves and experiments. So that's why there is a difference, because we're going into the zones where does isocratic and Van Deemter theory merge and agree with the maths, the complex mathematical equations when we jump into gradient elution reverse phase theory.
Okay. If later down the line before validation, you need to change the assay, for example, to create a method for higher throughput, how would you advise the use of this practical guide?
That's a good question, and definitely that's also pulling us in two directions, because as chromatographers, as separation scientists, we know that flow rate is really the driving aspect for throughput. So the good news for small molecules, you want to drive that as high as possible. For larger peptide molecules, you need to do that systematic experiments for velocity. However, when we look at the protocols, you know, if you go back to the peptide protocol, the gradient time is the first decision. So going back into the multivariate trends, we do need to make that throughput and gradient time decision right at the start. So if you're in a high throughput lab, I would say I would have a really honest and direct conversation with the project manager. How much time can I invest for every injection? How many injections do I need to make every day? Take into account you need to set some time for yourself for data analysis. So understand how high throughput you want to make. That's going to define your gradient time decision. And then later on, you're going to have your flow rate decision. But what that's going to do is really assist the gradient compression effect. And then the last decision is make sure you maximize that gradient time for your sample separation for both the peptide and the small molecule approach.
Okay. Unfortunately, I think that's all the time we're going to have for questions today. If you did have a question that we did not get to, we will follow up with you via email. I also just want to remind everyone there were a few questions about link to the recording and slides. We will send out an email that will have a link to the recording of the webinar as well as the slides. I also want to let you know that we do have an upcoming 3-part 20-minute webinar series on selectivity that will start in October. So be on the lookout for some emails on how to register for those. Thank you again, Ariane, for joining us, and thank you to everyone for attending. Have a great rest of your day, and we'll see you on the next broadcast. Thank you.